Welcome to our discussion of antiderivatives, what will become the beginning discussion of integrals, which is basically what you learn in a Calc 2 class. Antiderivatives are basically just the inverse of a derivative, just like the inverse cosine is sometimes called like an anti-cosine function. An antiderivative is just an inverse of a derivative. And it is literally defined that way, right? We define a function capital F as an antiderivative of lowercase f on some interval I. We always put it on an interval because sometimes we have to restrict domains in order to get one-to-one functions so that we can actually get an inverse. But anyhow, if f, right, big F prime, right? So this is now the derivative of the big F function is actually equal to little f, right? So the lowercase f function is the derivative of the big F function. So the big F function is the antiderivative of the little f function. We're just talking about inverses. The worst thing about this is when the math community decided to call the antiderivative function f as well. And the big F versus little f is just going to confuse the crap out of you. And unfortunately, it's just the nomenclature that is used, so get used to it. Try to just keep telling yourself that's the derivative of that, or that's the inverse derivative of that, if you want to think of it that way instead of the antiderivative. But the f's and f's and f's and f's will get confusing. That's the most confusing part about this whole idea, because you understand what an inverse function is, and that's all this is. It's an inverse function. So for instance, let's say little f, right, our normal function notation, little f is x squared. It's not too difficult to figure out what the antiderivative of little f would be if we just think about the power rule, right? The power rule, if we take the derivative of something, if you remember the derivative of x to the n is n x to the n minus 1, right? So if on the right hand side we have x cubed, what did the original function have to be to get us there? Well, you can see that if this is a 3, right, if n minus 1 equals 3, doesn't that mean n equals 4? So we had to start at x to the 4th. Sorry, I don't know why I'm doing cubes and squares, right? Well, let's go ahead and keep going with cubes. You can see the example up here with the square. So if we started with an x cubed and we wanted to go backwards, it's x to the 4th. But if we take the derivative of x to the 4th, we get 4x cubed. So in order to get rid of that 4, 1/4. And now when you take the derivative of it, doesn't the 4 cancel the 1/4? Ta-da, right? And then the same thing happens when we go from x squared backwards. We know it had to be x cubed, and then we throw this 1/3 in front of it so that when we take the derivative, the 3 cancels the 1/3. But you can also see that 1/3 x cubed plus 100, if you take the derivative of that, that also equals x squared because the 100 goes away. And in fact, 1/3 x cubed plus any constant will satisfy it. This should be down here. So anything of this form where c is any constant is going to be an antiderivative of f. Because if you take the derivative of 1/3 x cubed plus a constant, the constant goes away, and you just end up getting x squared. So we can see that the general antiderivative of our original function f is going to be 1/3 x cubed plus a constant. And that brings us to our theorem that if f is an antiderivative of little f on some interval, then the most general antiderivative of little f is going to be the big F function we just found plus a constant. And then if the function ends up not having a constant at all, for instance, in this case, if it was just 1/3 x cubed, then c is just 0, right? So plus c is the most general case, and it works for everything. So every antiderivative of little f can be written as big capital F plus a c. And if we look at the graph of 1/3 x cubed plus a bunch of different constants, you can see that it's the same curve that's just been shifted up and down, because that's what happens when you add a constant right to the end of a function. It just shifts it vertically. Well, if it's been shifted vertically, its shape hasn't been changed at all. And remember, a derivative of a function is something that describes the slope, the shape, right, the curvature of your original function. So if these functions all have the exact same shape, they're all going to have the exact same derivative, because the slope of the tangent line for any x, pick an x, let x be this point right here. That slope is the same as that slope is the same as that slope, and so on and so on. Let's look at an example. Let's find the most general antiderivative of each of the following functions: sine 1 over x and x to the n, where n is not a negative 1. Well, basically all you're doing is you're finding these inverses of what is a derivative. You're basically asking yourself, okay, sine is the derivative of what? 1 over x is the derivative of what, right? X to the n is the derivative of what? And then that ends up becoming your antiderivative. So what gets us sine when we take a derivative? And you remember, well, the derivative of cosine is minus sine, so minus cosine would get us sine. And then, of course, to make it the most general, we just slap a plus c on the end. And then 1 over x, we remember the derivative of natural log of x equals 1 over x. So on the interval 0 to infinity, because remember this function is only defined on 0 to infinity, the antiderivative of 1 over x is natural log of x plus c. We also learned that the derivative of the natural log of the absolute value of x equals 1 over x as long as x doesn't equal 0, because if we take the absolute value of x, it now lets us use negative numbers, right? We could, before we had to have values bigger than 0, we could do values less than 0 as long as we took the absolute value of them. And so in that case, we would just have the absolute value of x plus c on any interval that doesn't contain 0. So in particular, it's true for basically everything but 0. Negative infinity up to 0, and then 0 up to infinity. Either one. But if you want to choose just this interval, 0 to infinity, then you don't have to have the absolute values. You can just have the regular one. Okay? What about our last one? Or to sum up that, here's the idea that if x is greater than 0, we're getting natural log of just x. If it's less than, we're doing negative x. And then, of course, if you do the absolute value, it works for both. Okay, the last one, the power rule. We've already seen two examples. We saw that x squared went back to 1/3 x cubed. We saw that x cubed went back to 1/4 x to the 4th. And so now you can hopefully see that the antiderivative of x to the n is going to be x to the n plus 1 all over n plus 1, because when you take the derivative of this, the n plus 1 was going to come down and joink, cancel out with the n plus 1 that's there, and you're left with just x to the n. So this ends up being our generic antiderivative of x to the n, which is kind of nice because now we can find the antiderivative of any polynomial, because we're just doing, each term is just a power of x. Now this is only valid when our n, our power, is greater than 0, because then x to the n is defined on that interval, and if n is negative, right, minus, not equal to minus 1, it's valid on any interval that doesn't contain 0. As in our previous examples, we can kind of generalize a bunch of common derivatives, things that we already know. We know that the derivative of a constant times a function is a constant times the derivative of the function. So if we're trying to find the antiderivative of a constant times a function, it's just going to be a constant times that antiderivative. See, that's what this capital X means. Remember, it's defined as the antiderivative of the little one. And then if we know that the derivative of a sum is just the sum of the derivatives, so the same is going to work for the antiderivatives. These are each going to go back to each thing. We just figured out that this one works, right? N can't be -1 because then we're dividing by 0. We know 1 over x goes to natural log of the absolute value of x. And then, of course, that works for everything but 0. E to the x goes to e to the x, of course, because the derivative of e to the x is just e to the x. Cosine goes to sine because the derivative of sine is cosine, right? And sine to negative cosine. And we can do the same with the rest of the trig functions. And then we can also list like our inverse trig functions and our hyperbolics. Because anything that we know what the derivative is, we know what the antiderivative is. Because, again, just inverses, right? The derivative goes this way, d dx, and then the antiderivative. So the derivative of sine gets us back to cosine, and the antiderivative of cosine is sine. Inverse functions. Now, you can go through that formula and you can remind yourself or that table, and you can remind yourself of why these things are correct, and it just comes down from the basic rules of derivatives. If you have an equation that involves the derivative of a function, we call that a differential equation, and then the general solution of a differential equation is going to involve an arbitrary constant, because to solve a differential equation you have to anti-differentiate, and you're going to have that plus c. But you might be given some extra conditions that will allow you to determine what those constants actually are, and then therefore you can find a unique solution to your differential equation rather than the general equation of having that plus c. Now, anti-differentiation is very useful in analyzing motion of an object, because as we've seen before, the velocity of an object is the derivative of position, and then the acceleration is the derivative of velocity. And so we can go backwards from all those. If we know acceleration, we can anti-differentiate to come up with velocity, and then we can anti-differentiate to come up with position. But each of those steps would add a plus c. So we can only get a specific answer if we have extra information that will allow us to solve for those plus c's each time. Let's look at an example so you can see what I mean. So we're told that a particle moves in a straight line and has acceleration given by the simple function 6t plus 4. They also tell us that its initial velocity, that's what v of 0 means, because it's when time equals 0, its velocity is -6. And they also tell us its initial displacement, so s at time 0, s being the function for displacement. They use s a lot in physics instead of d or h or something like that. They use s, v, and a. So now we can find its position function s of t using all of this information. So very quickly and easily, we just anti-differentiate 6t plus 4. We use the power rule, and we know this goes up to t squared over 2. This constant just becomes a t, right? It basically goes from t to the 0 to t to the 1 over 1. And then we slap on a c, and then we clean it up, right? 6 divided by 2 is just this, and we get that equation for velocity. But we don't want c. We want to know what c actually is, which is very easy, because we know v of 0 equals -6. That means that if we plug 0 into this function, it should equal -6. So 3 of 0 squared plus 4 of times 0 plus c has to equal -6. Well, these all go away, and you basically get that c equals -6. And now you know specifically this is your function for velocity, 3t squared plus 4t minus 6 instead of just a plus c. Now we can anti-differentiate this to get acceleration. Again, use the power rule, right? So t to the 2 plus 1 over 2 plus 1. This goes to t to the 1 plus 1 over 1 plus 1. And then this gets a t slapped on it. And then we add a new constant. We can call this one d, or you can call it c sub 2 for a new constant. Clean it up. Do the same thing. We know the initial position is 9. And we also know it's going to equal d, because when you let all these be 0, they go away. and so that tells us that d equals 9, and we get the overall specific function for position rather than a general version. Okay? And it's really just that easy, guys. That's all we're doing with antiderivatives, is we're basically rewinding the clock. You're taking things and you're stepping them back to figure out the function that when you take the derivative of it, it would be the thing you're starting with, right? So you anti-differentiate velocity to get back to position. If you took the derivative of position, you would go right back to that velocity function.